In this video, we're going to go over section 9.1 from our textbook, which is on angles. We'll start with some basic terminology that we're all maybe familiar with, but it doesn't hurt to have a little refresher. So we'll start with this here. So two distinct points, A and B, determine the line denoted AB here. And so this is what this looks like visually. Now, a portion of the line, which includes points A and B, is going to be called the line segment AB and is given by this guy here. Now, the portion of the line that starts at A and continues through our point B is called a ray, and that'll be ray AB here. Now, an angle is formed by rotating a ray like this here, which we also call the initial side, around its endpoint or the vertex to its terminal side. So visually here, if we're looking at a positive angle, this ray here, CA, is our initial side, and we're rotating it around the end point of this ray, which is also going to be this vertex C here. And we stop right about here, so this is going to be our terminal side or our terminal ray. And this is a positive angle. We're rotating counterclockwise. Now, if we had a negative angle, we still have our initial side here, this ray. And now we're rotating in this direction. We're rotating clockwise, and this would be a negative angle, stopping here again at our terminal side here. Now, moving on to degree measure here. So degrees divide the circumference of a circle into 360 parts. So here is our circle, and so we have 360 degrees in one circle. Now, an acute angle is going to be an angle between 0 and 90 degrees. A right angle is an angle that is exactly 90 degrees. Now, an obtuse angle is an angle that is greater than 90, but less than 180 degrees. And a straight angle is an angle that is exactly 180 degrees. Now, we want to calculate with degrees, minutes, and seconds here. 1 minute is written as this here, and it is 1/60th of a degree. So, written like this, or we have that 60 minutes is going to be equal to 1 degree. Similarly, 1 second is written as this here, and it's 1/60th of a minute now. So this means 1 second is going to be 1/60th of a minute using the same notation up here, which is going to be 1 over 3600 degrees, or 60 seconds is equal to 1 minute. With this information, we'll look at this example here. We want to convert the following angle to decimal degree notation. So we have the angle 37 degrees and 60 minutes here. We know that 60 minutes is just equal to 1 degree here. So this can be written as the sum of 37 degrees and 1 degree here. So for this guy, we just get 38 degrees. So that's how we would solve a problem like this here. Now, there are many different types of angles. The first one we'll look at here is quadrantal angles. And so these are angles in standard position. So this means the vertex here is at our origin. The initial side is along our x-axis, or the positive x-axis, and our terminal sides are along the x or y axes here. So this means at 90 degrees, 180 degrees, 270 degrees, and so on. Okay, and then also notice here that these are our quadrants, so our 4 quadrants here, and we can see that our degrees in the first quadrant are between 0 and 90 degrees, and the second between 90 and 180, and so on and so forth. Now, another type of angles that we'll see are called coterminal angles. So these are angles that have the same initial side and the same terminal side, but different amounts of rotation. So this means their measure differs by multiples of 360 degrees. So for example here, we have this initial side and this terminal side here, and this angle here is 60 degrees. We just rotated from our initial side to this here, which would be 60 degrees. Now, if we did the same thing, but did a full rotation all the way up to here, we would no longer be at an angle of 60 degrees, but 60 plus 360 degrees, which would be 420 degrees. So they just differ by one extra rotation in this case. Now looking at this guy on the right here, we have our initial side along the positive x-axis and our terminal side here. So this angle right here is about 110 degrees, just going from this guy to this terminal side here. If we were to do the same thing, but add 2 extra degrees of rotation, we would get 830 degrees. Okay, so 60 degrees and 420 are coterminal angles, and 110 and 830 are coterminal angles because their measure just differs by a multiple of 360 degrees. So for example, if we wanted to find the angle of least positive measure coterminal with the angle A is equal to negative 97 degrees, we know that a coterminal angle for this guy is going to differ by a multiple of 360 degrees, and we want to find the angle of least positive measure. So this means what we'll do is we have negative 97 degrees, and we're going to add 360 degrees to this guy, because we know if an angle is coterminal with A here, they'll just differ by 360 degrees. Adding these guys together, we get 263 degrees. So this means that that angle would be coterminal with negative 97 degrees. And just looking at this figure here, if we have negative 97 degrees, our initial side's going to be somewhere around here, and we're rotating in this direction. Okay? So the angle of least positive measure coterminal with negative 97 degrees is going to have the same initial side and the same terminal side here. So it's going to be given by this guy here in green. This is 263 degrees. Now notice we didn't do a full rotation around our vertex, but these guys are still coterminal to each other because they do differ by a multiple of 360 degrees. Okay. Now let's look at the next example here. We want to find the measure of the least positive angle that is coterminal with 187 degrees here. So again, this guy is going to, the coterminal angle is going to differ by a multiple of 360 degrees. So adding 360 degrees to this guy, we'll get 547 degrees here. And we want to find the measure of the least positive angle. So we might think that maybe we could actually subtract 360 degrees. Doing so, we'll still get a coterminal angle to 187 because these guys just have to differ by a multiple of 360 degrees. So if we were to do 187 minus 360 degrees instead, we would in fact get a coterminal angle, negative 173 degrees. However, we were looking for the least positive angle in this case. So this is not going to be an option. Our answer will be 547 degrees here. So a general rule of thumb is that every coterminal angle to some angle A is given by this expression here, where n represents the number of rotations that we have. Alright, so moving on to radian measure here. We're told that an angle with its vertex at the center of a circle that intercepts an arc on the circle here, equal in length to the radius of the circle, given by this guy here, has a measure of 1 radian. Now the radian is a real number, where the degree is a unit of measurement. So the circumference of a circle is given by 2 pi r here, where r is going to be the radius of the circle. Now this shows that at an angle of 360 degrees, this circumference will have a measure of 2 pi radians. So this tells us that 360 degrees is equal to 2 pi, or 180 degrees is equal to 2 pi. Now something important to know is how to convert between degrees and radians. Now if we want to convert from degrees to radians, we'll multiply that degree by pi over 180 and simplify it. And then to convert from radians to degrees, we'll multiply by 180 over pi and simplify that guy. So, for example here, if you wanted to convert 33 degrees to radians, so 33 degrees, what we'll have to do is multiply this guy by pi over 180. And we can think of this as our units canceling out. We have degrees on the top and bottom, so these guys cancel, and we're left in units of radians, because this will be 33 pi over 180. Now to simplify this, we can divide the top and bottom by 3. We'll get 11 pi over 60. And so this will be approximately 0.58, rounding our final answer. Okay. So what we do here is we divide 11 by 60 here, and then multiply by pi, which is equal to approximately equal to 3.14. Similarly, if we want to convert 2 radians to 2 degrees, this is going to be 2 pi, and we got to multiply this by 180 degrees over pi. And again, we can think of this as our units canceling. We're left with degrees here because we'll have 2 times 180 degrees. And so 2 times 180 is going to be 360. And so that's also how we can show that 2 pi is equal to 360 degrees here. Alright, so this table below here gives our degrees and their exact radian and then approximate measurement here. And then this is our unit circle here, broken up into its degrees and radians, given by the blue and red measurements respectively. So this will come into play a little bit more in our next section. But for now, we're going to talk about arc length next. So the length S of the arc intercepted on a circle of radius r by a central angle of measurement theta radians here, so this guy is our Greek letter theta, is given by the product of the radius and the radian measure of the angle. Okay? So the length S of the arc here is given by the product of our radius and our angle measure here, so r times theta. So, for example, if you want to find the exact length of the arc intercepted by the given central angle in this figure below here, we'll use that formula. So in this case, it might be a little bit hard to see here, but theta is given by this angle here, and it's 3 pi over 5. And then r, our radius, is given by this guy here, and that's equal to 5. So this tells us our length, s, or our arc length, is going to be given by 5 times 3 pi over 5. And then in this case, our 5's cancel, and so this tells us our arc length is equal to 3 pi. Okay. This brings us to the area of a sector. So the area of a sector of a circle of radius r and central angle, again, theta, is going to be given by this formula here. So, for example, if we wanted to find the area of a sector of a circle having radius r and central angle below here, so our radius is 12.7 centimeters, and our central angle, theta, is equal to 70 degrees here. We'll use our formula above, so a is going to be equal to 1/2 times our radius squared, so 12.7 squared, times our theta. So in this case, that's 70 degrees. Alright, but notice in our formula here, it says that our angle theta here needs to be in radians. So before we can actually calculate this, we need to convert theta from degrees to radians. We know how to do that here. We just multiply it by pi over 180. We'll end up with 70 pi over 180. And then simplifying this by dividing by 10, we'll get 7 pi over 18. So we get that our area is going to be equal to 1/2 times 12.7 squared times 7 pi over 18. All right, now we can multiply this 1/2 and our 7 pi over 18 here to get 7 pi over 36. And then 12.7 squared is going to be 161.29. Multiplying this guy here, we'll get 98.476. So we could round this to approximately 98.5. Okay, so that would be the area of a sector of a circle having radius and central angle given by those guys there. All right. We also have what's called supplementary and complementary angles. So if the sum of two positive angles is 90 degrees, the angles are called complementary. And if the sum of two positive angles is 180 degrees, then the angles are called supplementary in this case. Okay. So for example here, if you wanted to find the complementary and supplementary angles to 3 pi over 8, we can use these definitions. However, since this angle is given in radians here, what I'll do is rewrite these definitions so we're looking at it in terms of radians. So for the complementary angle, the sum of two positive angles is 90 degrees. That's the same thing as saying that the sum of the two positive angles is equal to pi over 2. Similarly, for our supplementary angles, if the sum of two positive angles is 180, that's the same as saying the sum of these two positive angles is equal to pi here. All right, so going back to this example here, we'll first find the complementary angles. To 3 pi over 8. So this tells us that the sum of two angles, one of them being 3 pi over 8, the other being unknown, the one that we want to find, which I'll denote by n, is going to be equal to pi over 2. What we can do in this case is subtract 3 pi over 8 on both sides and solve for n. So we have that n is going to be equal to pi over 2 minus 3 pi over 8. This is the same thing as 4 pi over 8 minus 3 pi over 8. So this tells us that n is going to be equal to pi over 8. So this would be the complementary angle to 3 pi over 8. And on the other hand, the supplementary angle we know we're also going to represent this by n here. The sum of n and 3 pi over 8 needs to be equal to pi in this case. So doing the same thing here, solving for n, we get that n is going to be equal to pi minus 3 pi over 8. Pi can also be written as 8 pi over 8, so we have a common denominator just like we did for our complementary angle. And in this case, we get 5 pi over 8. So the supplementary angle to 3 pi over 8 is 5 pi over 8. Alright, and then the last thing that we'll do in this video is talk about linear and angular speed. So angular speed is given by this guy here. This is a new Greek letter. We call this guy omega. It's lowercase omega. And that's going to be our angular speed. And it's going to be equal to theta divided by time here, where theta is in radians, and again, t is our unit of time. Our linear speed here is going to be given by v, and it's going to be equal to s over t, where s is our arc length. Now remember, our arc length was equal to r times theta here. So we can rewrite this as our linear speed is equal to r times theta over t. And then remember, theta over t is equal to our omega here, or our angular speed. So this means we have r times omega would be equal to our linear speed. So we'll look at an example of this. We're told that a belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. And the first thing we want to do is find the angular speed of the pulley in radians per second. So for part A here, the first thing to note here is that looking at this pulley on the right-hand side here, each revolution, so each rotation of the sky, is going to be 360 degrees. So this is the same as 2 pi radians, because 360 degrees is equal to 2 pi. We showed that in a few examples ago. So if we want to find the angular speed in radians here, first thing we need to do is rewrite our 80 revolutions per minute as radians per minute. So if we do 80 revolutions per minute, we know that we're going around this circle 80 times in 1 minute, and this circle going around in 1 revolution is equivalent to 2 pi. So we'll do 80 times 2 pi here. This tells us we're going around 160 pi radians per minute. So every single minute we are going around this sky 80 times, and in units of radians, that's the same as 160 pi radians. So now we can calculate our angular speed here. This is going to be 160 pi radians per minute, and then in this case we want to find the angular speed of the pulley in radians per second. If we're going 160 pi radians per minute, this is the same as 160 pi radians per 60 seconds. Simplifying this guy here, we'll get 8 pi over 3 radians per second. Alright, and then for part B here, we want to find the linear speed of the belt in centimeters per second. Remember, our linear speed is given by either one of these guys here, or any one of these guys here. We just found our angular speed, and we know that our radius is going to be 6 centimeters. So what we'll do is we'll use this guy here. So our linear speed is going to be equal to our radius times our angular speed. We know that our radius, like we said, is 6 centimeters, so it'll be 6 times 8 pi over 3, that was the angular speed. This will be equal to 2 times 8 pi, so this will be 16 pi here, which is going to be roughly 50 centimeters per second. Alright, so that'll be it for this video.